Hi everyone, I'm Kiley Feickert, a graduate student at MIT, and today I'll be presenting a paper I co-wrote with Caitlin Mueller titled Thin Shell Foundations, Historical Review and Future Opportunities. As most of you probably know, this is the Mexico City airport designed by Foster and Partners in Free. It was unfortunately canceled in 2018. And as you can see, the foundations, which required extraordinary engineering and an extraordinary amount of material, had already been constructed. Due to the soft soil of the site, the foundations seen here were comprised of over 5,500 piles and a floating raft, which is 1.5 meters thick. This equates to approximately 1.1 million cubic meters of reinforced concrete, the environmental impact of which is quite substantial. The embodied carbon is estimated to account for over 1.2 million tons of carbon dioxide, which equates to the carbon emissions of over 260,000 passenger vehicles for a typical year in the US. Based on a study of 200 buildings, it was found that the substructure and foundations account for up to 40% of a building's embodied carbon. However, foundations are often overlooked when quantifying emissions, perhaps because they're not typically seen. Prismatic foundations work in bending, which is an inefficient method of load transfer. This requires that the foundations are large enough to spread the building load to the soil below, and are also substantially thick in order to resist bending. At the same time, if global warming is to be limited to 1.5 degrees Celsius above pre-industrial levels, it's imperative to consider the environmental impact of foundations more seriously, since they're one of the biggest contributors of embodied carbon on a project. Much work has been done on materially efficient floor systems, including shaped slabs by Ismail and Mueller and the Beyond Bending project shown here. This research takes a similar approach, where shell foundations are proposed to better utilize the material cross-section, reducing its quantity and ultimately reducing embodied carbon. A historical review of materially efficient foundations led to shell foundations, and although advanced work has been completed on them, the environmental impact has not been quantified. So this work does so, and it also proposes digital fabrication methods for their implementation. The first built example of a shell foundation brings us back to Mexico City, where Felix Candela, one of the most prolific builders of shell foundations, built this prototype in 1953. In the same year, he used hyperbolic paraboloid shells for the foundations of the customs warehouse, also in Mexico City. Although the savings weren't quantified, Candela highlighted that significant material savings were achieved, substantially reducing the cost. Most of the built examples to date have been motivated by saving cost, in contexts where material costs outweigh labor costs. However, since environmental impact is based on material quantities, it's important to consider design strategies for the future that reduce material consumption and embodied carbon in all contexts. The design of shell foundations is not well known in most of the world. However, Professor Nainan Kirian has published extensively on the topic. He's responsible for the only building code dedicated to shell foundations, which is in India, and the textbook seen here. For the embodied carbon analysis, I'll be focusing on hyperbolic paraboloid shells, or HYPARs. Their geometry is classified by doubly curved anticlastic quadrants that can be constructed using straight lines in either direction, making them strong candidates both for strength and fabrication. Existing methodologies were used to design spread fittings, and the methodology developed by Kirian was used for a HYPAR fitting for the same column load. We then wrote code to compute the calculations for a variety of geotechnical and structural conditions in order to evaluate the resulting material quantities and embodied carbon. We found that the HYPAR fitting saves a significant amount of embodied carbon when compared to the spread fitting for the same load. For a column load of 2 meganewtons, which equates to about a 4-story building made of a composite metal deck and concrete slab, the HYPAR saves 64% of embodied carbon, and the performance improves for higher loads. For example, the shell saves 72% of embodied carbon for a 5 meganewton load. The reduction in embodied carbon is entirely due to the significant reduction in concrete. Taking the same loads, a shell supporting a 2 meganewton load saves 76%, while a shell supporting a 5 meganewton load saves 83% of concrete. One area where the HYPAR fitting does not outperform the spread fitting is the required steel quantities. In this case, the HYPAR uses 55% more steel for a 5 meganewton load. However, this is an area that's ripe for future study. The edge beams and the ridge beams were designed to be prismatic, although the compression and tension forces reduced to zero along their length. This means that these elements can be shape optimized to further reduce both the steel and the concrete quantities required to support the same load. Foundations also provide an opportunity to be economically built using today's digital fabrication techniques. Local earth can be utilized as formwork, reducing the requirement for additional materials. This has been deployed at large scale, such as the Teshima Art Museum in Japan. And advances in 3D printing, such as 3D printing earth, offer pathways to addressing the additional time and labor required to shape the soil to receive more complex geometry. We're currently in the process of applying methods developed by fellow MIT researchers, Kurth and Gonzalez, for 3D printing clay to act as formwork, which we hope to test shortly. In conclusion, this paper contributes a historical overview of shell foundations. It also quantifies their environmental impact. We found that shell foundations save 72% of embodied carbon and 85% of concrete compared to a prismatic foundation, supporting the same load. Lastly, it proposes 3D printing earth as a pathway to manufacturing complex forms while reducing labor. And while I'm not necessarily proposing shell foundations for all projects moving forward, I do believe that as architects and engineers, we must consider alternative solutions to existing systems, such as these foundations, in order to limit our environmental impact and reduce embodied carbon in buildings. Thank you.